Hello students, today we will start the beta function. In the previous classes we have completed the gamma function and its various forms. So in this chapter we will learn the definition of beta function, different forms of the beta function, relation of beta function with the gamma function. This is the most important result and some of the integrals we will evaluate. Okay, let us start the beta function. First we give the definition of beta function. The definition will be the definition of beta function as follows. The definition of beta function. Beta mn. It is the integration with the limits from 0 to 1. It is the integration with the limits from 0 to 1 t power m minus 1 into 1 minus t power n minus 1 of course dt. T is a variable here which varies from 0 to 1. The lower limit of t is 0 and upper limit is 1. Here where m and n are integer values that are greater than 0. Positive integral values, even they can be fractions also. Greater than 0 means it can be 1, 2, 3, 4, 5 and it can be 1 by 2, 1 by 3, 1 by 4, 1 by 5, 2 by 3 like that also. So must be positive numbers. So in general speaking, m and n are the complex numbers. They are the real value. A complex number real argument. So anyway, we will not consider the complex numbers here. We will consider on the real values. So that here m and n will be just simply the positive numbers which are greater than 0. So this is the fundamental definition of beta function. You should remember this. So we will see the other forms of it. Other forms of beta function. Other forms of beta function. Other forms are, you can say, these are the properties, whatever it may be. So the first thing I'll observe, what is the first thing I'll observe here? The first thing will be beta mn will be equal to beta nm. So proving here it is a symmetric function. It is a symmetric function. It is a symmetric function. Let us see how we will derive this. We will start from the basic definition of the beta function. We know beta mn will be is equal to 0 to 1 t power m minus 1 1 minus t whole power n minus 1 into dt. So what I will do here, put y is equal to 1 minus t. I will substitute y is equal to 1 minus t. Then obviously dy will be is equal to minus dt, differentiation. Now let's see the limits. When t will be 0, y will be 1. When t will be 1, then y will be 0. So with this, what happens to our function? So this beta mn will become lower limit. When t will be 0, y will be 1. Lower limit is 1 and upper limit will be 0. But in place of t, I need to substitute. In place of t, I need to substitute 1 minus y here. Whole power m minus 1. In place of 1 minus t, it is by power n minus 1. In place of dt, it will be of minus dt. So wherever dt is there, I need to substitute the minus dy. See here it is dt is there, in place of dt minus dy. So here 1 minus t is there, I substituted y. But in place of t here, I need to substitute t. Bring t this side and y to that side. It will become 1 minus y. Okay, I hope it is clear. Now let us see the further. Here what can I write here? So this is the beta mn. So with this minus sign, whatever the minus sign I have here, this is the minus sign. With this minus sign, I can interchange the limits. So here you eliminate the minus sign here, eliminate the minus sign here, and you change the limits will be here. Lower limit will become upper limit and upper limit will become lower limit. So that means, so what I have here, so beta mn will be is equal to, change the limits 0 to 1, and I'll put first y, this term I'll put, so y into n minus 1, next I'll put this term will be 1 minus y into whole power m minus 1. So, clearly whole power m minus 1. So clearly this will be is equal to, again the standard definition of beta function, with here it is, instead of m minus 1 we have n minus 1, and here instead of n minus 1 we have m minus 1. That's it. So very easily proved, quite easily done. So what we have started here, we have proved the beta function is a symmetric function. Okay, so very simple to prove. So what I taken here, this definition of the beta function I have taken. So after taking the definition of beta function, so I just substituted, put y is equal to 1 minus t and dy is equal to minus dt, and the limits what we have seen here. So limits also, so very clearly mentioned here what are the limits and everything. So then we have limits 1 to 0 in place of t. So here y is equal to 1 minus t we have taken. T I want to bring t will be this side and y will be this side, 1 minus y. In place of 1 minus t there will be y. In place of dt there will be minus dy, and so rest. Okay. So remember the definition of the beta function and the symmetric function it is we have proved. Okay. Thank you. Hello students, welcome back. So we are discussing various forms of the beta function. So second form of the beta function will be, our second property of the beta function will be, the second one as follows, that is important for us. It is of beta mn will be is equal to 0 to infinity u power m minus 1 divided by 1 plus u into whole power m plus n, of course d. This we need to prove here. So very easy to prove. For that purpose, again always remember, first we start from the definition. So with the definition only we can do anything. So what the definition will be? The definition as follows. The definition of beta function will be, beta mn will be is equal to 0 to 1. So t power m minus 1, 1 minus t whole power n minus 1 into dt. So somehow we have to convert here t into use, and n will not appear on the numerator. So with that, what I do here, so it's very simple. I'll substitute something here. Let us put t is equal to u upon 1 plus u. First it is the limits here. So when t will be 0, then what will be the u? So this can be written as like this. So t is equal to 1 by 1 plus 1 by u, also correct. So 1 plus 1 by u I wrote here. Now let us substitute u equal to infinity. Limit tends to infinity, somewhat like limit tends to infinity. So u tends to infinity. Our substitute u will be equal to infinity. Then what happens here? So here 1 by infinity 0. So 1 plus 0 is 1. So t will be 1. Let us substitute u will be 0. So 1 by 0 infinity, 1 plus infinity, 1 by infinity will be 0. T is equal to 0. This is the important thing here. So what I did here, we are taking t is equal to u by 1 plus u, or otherwise 1 by 1 plus 1 by u. Then see the limits at second one. So then obviously we required in place of dt what to substitute. So that is very easy. So now what I can do here, so dt. So dt will be is equal to, that means differentiation of this. So we have to use the formula of division formula 1 by 1 plus. So if I use the division formula, it will be 1 plus 1 by u whole square. So 1 plus u into 1 minus, then what I have, u into 1 plus u differentiation will be 1. So u will cancel, then left will be dt is equal to 1 by 1 plus u whole square. Of course don't forget to write d. Okay, I got what to write for dt also and what to write for limits also. Then proceed. Then come back to our original equation. So beta mn will be is equal to, limits will be, when t is 0 u is again 0, when t is 1 and u is infinity, in place of t I need to substitute u by 1 plus u by 1 plus u whole power m minus 1, but in place of 1 minus t, 1 minus, in place of t, u by 1 plus u whole power n minus 1, but in place of dt, it will be du divided by 1 plus u whole square. Okay, be careful what I have written here. So I just substituted all the values. Okay, now come to here. So just I'll simplify. So beta mn will be is equal to, so beta mn will be is equal to, no changes in the limits, equal to 0 to infinity. And then what I have here, u power m minus 1 divided by 1 plus u whole power m minus 1. You just simplify here. Take the LCM is 1 plus u. 1 plus u goes here. U will be cancelled. Only 1 is remaining. 1 power anything will be again 1. So I have 1 plus u whole power n minus 1. And here I have only du divided by 1 plus u whole square. So you observe the denominator I have. So beta mn will be is equal to limits from 0 to infinity u equal to 0 to infinity. So I have u power in the numerator, it is simply u power m minus 1 divided by denominator 1 plus u, 1 plus u, 1 plus u. So we can add the simply powers. So here it is m minus 1 plus n minus 1 plus 2. Of course don't forget to write d. So in the denominator minus 1 minus 1 minus 2 plus 2 cancel. I have left beta mn will be is equal to, u is equal to 0 to infinity u power m minus 1 divided by 1 plus u whole power m plus n. So very easily proved, quite easily done. Okay, I hope it is clear. Thank you. Welcome back, students. So we are discussing various forms of beta function or properties of the beta function. The third one will be, so what we need to prove here. We need to prove, so beta mn will be is equal to 0 to 1, the numerator u power m minus 1 plus u power n minus 1 divided by denominator 1 plus u whole power m plus n du. This we need to prove. Then again it is very simple to prove. So we will start from our previous. So we know beta mn will be is equal to, we know this here. We just now we prove this, 0 to infinity u power m minus 1 divided by 1 plus u whole power m plus 1 into du. So here we'll split the limits. It is from 0 to infinity now. Split from 0 to 1, then and 1 to infinity, and split the limits will be here. If I split the limits here, it is something 0 to 1 u power m minus 1 by, so 1 plus u whole power m plus n into du plus then 1 to infinity u power m minus 1 divided by 1 plus u into whole power m plus n du. So mainly our goal will be here on this integral. So this integral. So this integral, I'll take this integral as I. Then I proceed. Let us take this will be equal to I. Then we'll proceed. Then how to proceed here? And how to proceed here? So we have taken that will be equal to I. Then do one thing. So in this integral you substitute. What you substitute here? Let us put in this integral you substitute. Put. So what you put here? In this integral, put u is equal to 1 by y. Wherever u is there you substitute 1 by y. So then du obviously will be equal to minus 1 by y square into dy. So du will become minus 1 by y square into du. Then what the limits will be? When u will be 1 and y is also 1. So limits I'll write here. So when u is equal to 1, then y also will be, when u is equal to 1, then y also equal to 1. When u is equal to 1, when u is equal to 1, y is also 1. Then what about when u will become infinity, then y will become 0. So when u will become infinity, definitely y has to become 0. Okay, I got the limits also, so nothing to worry. I got the limits also here. Now what happens to this integral? So first we'll concentrate on this integral. As I said already, I have taken it as I. So this integral will become, so this integral will become, this integral will become this integral will become, so limits will change here. I will be is equal to, what are the limits? In place of when u will be 1 and y is 1, when u will be infinity, y will be 0 here. In place of u I am substituting 1 by y whole power m minus 1 divided by 1 plus 1 by y whole power m plus n into, in place of du we need to substitute minus 1 by y square into dy. Okay, I hope it is clear. Now just rearrange the terms, you will get the answer. I am just rearranging the terms. This minus sign, whatever the minus sign will be here, but I'll eliminate this minus sign and I'll interchange the limits. So next step will be is equal to, limits will be interchange 0 to 1. Then what will be here? You take the, here it is, this y will come down. So in the numerator we have dy Now come to denominator. This y power m minus 1 will be here. Then here it is y plus 1 by y whole power m plus n. Then here it will be 1 by y square. Now you clearly observe this y term will go up. So y term this will go up. So with this, so I will be is equal to, so with this I will be is equal to 0 to 1. This y term will go up. So y power m plus n into dy divided by, so y power I have here m minus n, and here it will be m minus 1, and here I have it will be plus 2. Okay, then what I left here, then I will be equal to 0 to 1 y power m plus n into dy divided by, and of course I forgot one term will be here, that will be 1 plus y whole power m plus n. So in the denominator what I have, y power m plus 1, so that is 1 plus y into whole power m plus n. So okay, I just rearrange all the terms here. So now if we clearly observe, in the numerator also y power m is there, in the denominator also y power m is there, that will be cancelled, and y power 1 will go up, so that will become y power m. So the next step will be 0 to 1, this y will go upward, so y power m plus n minus m minus 1, of course dy divided by 1 plus y whole power m plus n. So now what I have, so in this, so here it will be of plus n will be remain here, but my m and minus m will be cancelled with each other. So with that what I left here, so I will be is equal to, so 0 to 1 y power n minus 1 divided by 1 plus y whole power m plus n. So you can change any value here. Y is a dummy variable, so I can replace y with u. So y with u, it is the dummy index. So with the dummy index we can replace. So if I replace that, it will be is equal to 0 to 1. So y power, so in place of y I am writing u. 0 to 1. So it is u power n minus 1 divided by 1 plus u power m plus n. So finally our integral, whatever I have taken, so this I have taken here, so this integral, this entire one we have simplified, and finally we got that integral as this one. So we have got as this one. So finally what we write here, so finally we write here, so finally we have, so beta mn will be is equal to 0 to 1 u power m minus 1 divided by 1 plus u whole power m plus n, plus this integral will become again 0 to 1 u power n minus 1 by 1 plus u whole power m plus n. So even this can be written as, so beta mn will be is equal to 0 to 1. So the numerator u power m minus 1 plus u power n minus 1 divided by 1 plus u power m plus n, and of course u. So this is again an important result you need to remember. for future problem solving purpose. Okay guys, thank you. Welcome back students. We are discussing other forms of the beta function or various properties of the beta function. In this connection, next we have the other property of the beta function. So that as follows. Beta mn will be is equal to a power m b power n 0 to infinity x power m minus 1 divided by ax plus b whole power m plus 1 and of course dx. This is the other form of the beta function that we need to prove here. So then again very simple to prove. So we'll start from here. We know just now we proved beta mn will be is equal to 0 to infinity because the limits will be 0 to u power m minus 1 divided by 1 plus u whole power m plus n into du. Okay, now we need to substitute something to change the values. So what I do here, let us substitute. So let us put what I put u is equal to, I need a by b into x. So a by b into x. So clearly du will become a by b into dx, no changes. And of course limits also will not change. When u will be 0, x is 0. When u will be infinity, x is also infinity. No changes in the limits. So with this, what I have, so beta mn will be is equal to 0 to infinity. In place of u, I am substituting a by b x whole power m minus 1 divided by, in place of, here it will be, so 1 plus a by b into x whole power m plus n. But in place of du, a by b into dx. So after the substitution, just we need to simplify here. So beta mn will become, so 0 to infinity. So what I have here left, a by b will be here, also one a by b is here. So now you do one thing. So a by b here and a by b here. Here it is a by b whole power m minus 1. But this a by b whole power 1, that is plus 1. And x power m minus 1 dx divided by, the denominator I have b plus ax whole divided by b whole power m plus n. Okay guys, is it clear? I just rearrange the terms, all the terms. So now what I'll do now here, so a by b whole power minus 1 plus 1 will be cancelled here. X power m minus 1 you leave like that only, and this b you bring into above. This b will be coming up. So that means beta mn will be is equal to, so this a by b whole power m, this also comes up, that is beta power m plus n. Then limits will be 0 to infinity, nothing left here, x power m minus 1 divided by ax plus b whole power m plus 1 into dx. Okay, now let's see b power m here, and here also b power m is there, and b power m cancel, and what I left here will be here. So a power m and b power n, so 0 to infinity x power m minus 1 by ax plus b whole power m plus 1 into dx. Okay, so very easily done, quite easily done. Okay, thank you guys, I hope you understood. Hello students, welcome back. We'll discuss here another property or another form of beta function, or otherwise this is also called relationship between beta function and gamma function, and one of the important topic this. So with the help of this relation we can solve many problems. So what we need to prove here, I'll write that. So we need to prove here. So beta mn will be is equal to gamma m gamma n divided by gamma m plus n. This we need to prove here. So the way we will follow here, simple, will take the definition of gamma function and will proceed. That is one method, or another method, take the beta function and then proceed. So starting with the beta function, arriving the beta function in terms of gamma, or otherwise taking the gamma function and doing some algebra and finally arriving the beta function. So beta to gamma we can come, or gamma to beta we can come. So here first I will take beta function, and then from beta function I will go to the gamma function. Okay, let's proceed. So first we'll take the definition of beta function. We'll start from here. So we know beta mn will be is equal to 0 to 1 minus t whole power n minus 1 t power m minus 1 into dt. So here we do the integration by parts. Integration by parts. So in this integration by parts, what is the first term and what is the second term? I'll take, this will be the first term, 1 minus t will be the first term, and this will be the second term. This will be the second term. So integration by parts, I have beta m1 will be is equal to first term integration of the second term. Integration of second term will be t power m minus 1. Integration of this will be t power m minus 1 plus 1 divided by m minus 1 plus 1. That is integration of x power n formula, x power n plus 1 by n plus 1. So with that I have, so t power m by m. Remember, limits will be, lower limit is 0 and upper limit will be 1. Then minus integration of, so integration of the second term, then again I will get t power m divided by m into differentiation of the first term. Differentiation of the first term, that is x power n differentiation. So here is x power n differentiation, n into x power n minus 1, n into, that is n minus 1 into x power n minus 1. So n minus 1 means n minus 2. Then again 1 minus t differentiation, 1 differentiation will be 0, minus t differentiation will be minus dt. Okay. Then observe here, one of the important thing will be, what you need to observe here. So here when I substitute the limits, when I substitute the upper limit, in place of t will be 1. So I have need to substitute here, in place of t I need to substitute here. So when I substitute upper limit, it will become 1 minus 1. So 1 minus 1 power n minus 1, the rest of the thing. So that is obviously 0. Then I will substitute the lower limit. Lower limit means 0. So when I substitute here, so 0 power m divided by m, and the rest of the things, it will become 0. So that means if I substitute the upper limit or otherwise lower limit, both I am getting as the zeros here. So finally what I can say here, this entire thing will become 0. So what I have left here, so beta mn will be is equal to, this entire thing will be 0. Then one more thing, this is the minus sign here, and with this minus sign, and already here is the minus sign, this both will become plus. So what I have, integration from 0 to 1. Inside I have left n minus 1 in the numerator, m in the denominator, and t power m. So 1 minus t n minus 2 t power m into dt. You pull this outside, then beta m1 will become, so n minus 1 by m, then the remaining thing will be 0 to 1, 1 minus t whole power n minus 2 t power m into dt. Then again you proceed in the same manner. So integration by parts. Integration by parts. So with the first term, so this is the first term, and this will be the second term. So as usual, integration by parts, first term and second term. Then what I have, integration by parts. Then what I have, so beta mn, so beta mn will be is equal to, so n minus 1 by m. Now start from the integration by parts. So then again first term you keep as it is, integration of second term, so t power m plus 1 by denominator m plus 1. Okay, this is the second term. Integration of this will be t power m plus 1 by m plus 1. Then what I have here, 1 minus t whole power n minus 2 t power m plus 1 by m plus 1. Then again limits will be from 0 to 1, and of course here is a big bracket. Then minus integration from 0 to 1, integration of that will be again t power m plus 1 by m plus 1. Then differentiation of the second term, what I have, n minus 2 into 1 minus t into the t power n minus 3, and of course then that will be how d minus dt. Okay, okay. Now as usual, previously I said, so what happens here, if I substitute the upper limit, so upper limit in this place 1 minus 1 will come, it will become 0. If I substitute the lower limit, in this place 0 will come and this will become 0. So finally what I left will be here, so beta m1 will be is equal to n minus 1 by m, that entire thing will be 0. And of course here it is a minus sign will be here, this minus sign will become plus. I left with 0 to 1. So what is there, n minus 2 divided by m plus 1, 1 minus t whole power n minus 3 t power m plus 1 into dt. Okay, so now you bring this into outside. So finally what I have, so beta mn will be is equal to, in the numerator n minus 1 n minus 2, in the denominator m into m plus 1. As usual, limits from 0 to 1, 1 minus t whole power n minus 3 t power m plus 1 to dt. Then again continue the same manner, integration by parts. It will be integration by parts, continuing in the same manner. So continuing in this manner, continuing this process, what we get, continuing this process we get, so then again this will be the first term and this will be the second term, like this, continuing this process, what we get, so we get what we get here, we get, so beta mn will be equal to, first time it will be n minus 1, in the down it will be m, second time it will be n minus 2, here it will be m plus 1, then n minus 3, then here it will be m plus 2, m plus 2. So you observe here, it is n minus 1 and here it will be m, n minus 2 plus 1, n minus 3 plus 2, and so on, n minus 4, n minus 5, n minus 6, and so on, 2 and 1. We don't take the 0. Then in this also m plus 1, m plus 2, m plus 3, m plus 4, and ending will be m plus n minus 2, m plus n minus 2, with the integration from 0 to 1, t power m plus n minus 2 into dt. So okay, that 1 minus t whole power n minus 3, next it will come n minus 4, n minus 5, n minus 6, n minus 7, and so on and so on and so on. One of the instant it will become n minus something, that something is same as that of n, it will become 0. So 1 minus t power 0 will be 1, then that time only t power will be remaining. Okay guys, so now what I will do here, now I will integrate this. Now we need to integrate this. Integration something like simply x power n plus 1 by n plus 1, upper limit and lower limit we substitute here. So I will do here only. So if I do this, t power m plus n plus 1, so that is minus 1, divided by m plus n minus 1, with lower limit is 0 and upper limit is 1. So if I substitute lower limit and upper limit here, upper limit 1 power something, it will be 1. So 1 by m plus n minus 1, then minus lower limit 0 power something, it will be 0, m plus n minus 1. So then what I left here, it is simply 1 plus n minus 1. So this entire integration will be, I am getting this one. So finally what I have, finally we have, so beta mn will be is equal to, in the numerator n minus 1 term, n minus 2 term, n minus 3 term, and so on to 1, divided by in the denominator m into m plus 1 into m plus 2, and so on, m plus n minus 2, and one more term from the integration from here, it will be m plus n minus 1. Okay, so with that, so we are doing this integration here separately. So with that, what I will do here, so what I will do here, this anyway, this entire thing will become n minus 1 factorial. So in the denominator also I need to bring some factorial. So for that purpose, multiply and divide with m minus 1 factorial. Multiply and divide with m minus 1 factorial. We will multiply and divide with m minus 1 factorial. So with that, what I have, beta mn will be is equal to, so m minus 1 factorial, so this will be m minus 1, m minus 1 factorial, then I have n minus 1, n minus 2, n minus 3, and so on to 1, divided by the denominator I have m into, what is it, m into in the denominator I have m plus n minus 1, m plus n minus 2, m plus n minus 3, and so on, n minus 3, n minus 4, n minus 5, something like this. So I may get m plus 1, m plus 1, like that. So and so on, this is. So what I have finally here, beta, sorry, so what I have finally here, beta mn will be equal to this m minus 1 factorial and this entire thing n minus 1, n minus 2, n minus 3, that will become n minus 1 factorial whole divided by, here if you observe it is m plus n minus 1 minus 2, that's something like n factorial means n into n minus 1 into n minus 2 into n minus 3 into n minus 4 something. So m plus n minus 1 factorial. So we know the definition. So we know the definition of gamma function. So this is clearly beta mn will be is equal to m minus n factorial means it is simply gamma m. It is simply gamma n whole divided by so gamma m plus n. So because since so gamma m will be is equal to m minus 1 factorial, or otherwise we might have remembered this will be like this. Gamma n plus 1 will be is equal to n in something gamma sorry so gamma n will be is equal to n minus 1 factorial. So we have proved. So be careful. So we have started from the beta function definition. See here. So we have started from the beta function definition. And what we did here, we take first term and second term here and applied the integration by parts. So first time we applied, then again second time we applied here. Then after that what we have analyzed, continuing in this process, I get in the numerator this term and denominator will be this term and so on like this. And finally this integration, and then again after simplifying I'll get this m minus 1 factorial by n minus 1 factorial, m plus n minus 1 factorial, and finally we got this. Okay guys, I hope understood. You practice once. Okay, thank you. Welcome back students. In the previous video we have arrived a result. That result is relation between the beta function and gamma function. That result is so beta mn will be equal to gamma m gamma n divided by gamma m plus n. We arrived at the result. We started from beta function and derived the gamma, beta in terms of gamma. Now what we will do, we will start from the definition of the gamma function and we will end with the beta function. Okay, let us see how we will do. So we know, starting from the gamma function, we know so n factorial will be is equal to 0 to infinity e power minus x x power n dx. This is same as that of gamma n plus 1. Also m factorial will be is equal to 0 to infinity e power minus y power m dy. This will be gamma n plus 1. Now what I will do, take the product of these two. I am taking the product of these two. So that is n factorial into m factorial will be is equal to, I'll write like this, limit, I am introducing a parameter lambda that is tends to infinity, limit lambda tends to infinity 0 to lambda e power, when I take the product of these two, this one and this one, I am taking the product of these two things. So what I will have, e power minus x plus y. Then what is left? X power n. Then what is left? Y power m. Then obviously dx dy terms. Okay, I hope up to here it is clear. What I did here, I just introduced a variable lambda. With this integral, lower limit is 0 as usual, but upper limit will be changing to lambda, but lambda itself is limit lambda tends to infinity. Okay, no changes I made. I just introduced the limit, that is we have to evaluate this entire integral with the condition lambda tends to infinity. Okay, now what I'll do, now in this, what I'll do here, put this is important, put x plus y is equal to z and eliminate x. So in the place of x plus y you put z and eliminate x, that means x can be written as z minus y. In place of x we can substitute z minus y. With that what I'll get there, so n factorial left hand side as it is and m factorial, this limiting value lambda tends to infinity, now changes here. So 0 to lambda e power x plus y means it is z. I am eliminating the x, so x can be written as z minus y whole power n, then y there is no change, y power m. So keeping, then dx will become dz, dy no changes. Okay guys, now and one important thing will be careful here with the limits. So with the limits will be important here, how this limits will be changed, because we have introduced x plus y is equal to z, then even the limits also will change here. So that limits also will change. I'll substitute what are that limits, how it will change. So this can be written as n factorial m factorial limit lambda tends to infinity. So 0 to lambda dz I am writing here. So then limits will be for y. So y ranging from 0 to z. So least value of y will be 0 and highest value will be z. So with that what I have here, e power minus z minus y whole power n y power m into dy. Now what I'll do here, so this is the important thing here. What I'll do here in this, let us put here, put y equal to tz. In place of y substitute the dz, but in place of dy I'll put dt into z. Then limits, when y will be 0, t again 0. So when y is 0, t will be 0. So when y will be z, then what about when y will be z, t will become 1. Okay, be careful here, the limits will be very big careful. So with that what I have, so with that this result will become, so finally here n factorial m factorial as it is, sorry, what I have, this n factorial, so m factorial, of course limit lambda tends to infinity, that tends to infinity, of course here 0 to lambda dz, here y ranging from 0 to z, e power z as it is, but in place of y I had to substitute tz whole power n, but here in place of y tz whole power n, in place of dy I need to substitute dt into z. I hope it is clear to everyone. Okay, now here n factorial m factorial will be is equal to the right hand side limit lambda tends to infinity 0 to lambda. See the count here, z power n will come, and here also z power n is there. but here it will be in place of y here, sorry, here it will be m. Here it will be m. Here it will be m. So what I have here, e power minus z, all z powers, z power n here, z power m here, z power 1 here, z power m plus n plus 1. Then of course what I left here, 0 to y is equal to 0 to z. Then what is left? This entire integration I am writing here. E power z is gone. Then left will be 1 minus t whole power n, t power n into dt. Okay. Now limits you need to substitute here. You first substitute the limits here. Limits. When y is 0, t will become 0. When y is equal to z, t will become 1. That limits we need to substitute here. So t will become 1. Okay. Now with this, what I have finally, so n factorial m factorial is equal to limit lambda tends to infinity. Entire thing I am writing 0 to lambda e power minus z, z power m plus n plus 1, and of course dz here. Then the next integral will be only in terms of t, that is t is equal to 0 to 1, 1 minus t whole power n, t power m into dt. So you observe clearly here, this is the beta function. This is the beta function. This is the beta function. So then what about this integral? This integral will be evaluated as usual. So e power minus z into z power m plus n. So when we integrate this, so I had many times I said this type of integrals can be calculated with lambda equal to infinity. This integration will I'll get as 1 by, sorry, so it will be m plus n plus 1 factorial. So this entire integral will be, that is many times I said e power minus f of x into differentiation of that will be there. Then what to do? Okay, then again substitute the lambda is equal to infinity, then we'll get that. So finally I have, so n factorial into m factorial will be is equal to m plus n plus 1 factorial into 0 to 1, 1 minus t whole power n, t power m into dt. 0 to 1, 1 minus t whole power n, t power m into dt. So this I already said. So bring back this term will be here. Then what I have, n factorial divided by m plus n plus 1 factorial is equal to 0 to 1, 1 minus t whole power n, t power m into dt. So very clear. So what is this n factorial means? Gamma m plus 1, gamma n plus 1 by gamma n plus n plus 2. Okay. So this can be written as gamma n plus 1, gamma m plus 1 divided by gamma m plus 2. That will be is equal to, this is simply beta function with m replaced with m plus 1 and n replaced with n plus 1, because here we are supposed to have n minus 1 and here we are supposed to have m minus 1, but one decrease is one, here one plus is there, m minus 1 supposed to be there, we have plus 1, it's a plus 1. Okay, done guys. So even this, sorry, here That is n will be there. Gamma m plus n plus 2. Okay, we can rearrange, then we'll get the same answer. Okay, thank you. So finally learned from gamma to beta and beta to gamma that relationship. You can proceed in any manner. Thank you.